So last time we started into the math review. We pretty much did some algebra, reviewed over algebra, everything we're going to have to know for this course. Of course, basic algebra, given some equation with one variable, can you solve for the variable? We did quadratic equations, and just to remember the quadratic one, because that one has a little formula associated. That says if you have some equation of the form ax squared plus bx plus c is equal to 0, and you want to solve for the value of x, then the quadratic formula says x will be equal to minus b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. And this formula will give you two answers for the value. Now, what you're going to find when you do this on an actual problem, let's say a good example would be you're standing on a cliff with a rock. You throw the rock with a speed of 20 meters per second and an angle of 30 degrees off the cliff. The cliff is 10 meters high. And you'd like to know how long will it take for the rock to hit the ground. And you'll get an equation that looks like this, except instead of x's, it's t's. So t for time. And so you'll use a quadratic formula to solve for t, and you'll get two answers. The problem is, you know that in real life, when you throw a rock off a cliff, it only hits the ground at one time. There's not two different times where it hits the ground, it's just once. So what we have to do as a scientist, given the math gave us two answers, we have to use our logic to say which of those two answers is the right answer. Now, thankfully, it turns out to be easy. Because what could have happened, we could live in a universe where when we do this, we get 3.2 seconds and 4.1 seconds. Well, how in the world do you know which one is right? I mean, they both sound fine. Thankfully, what you're going to find when this pops up is you're probably going to get something like 3.2 seconds and negative 6 seconds. Well, obviously, negative 6 seconds doesn't make sense. The negative time, that means the rock hit the ground 6 seconds before you threw it. That doesn't make sense. So you can get rid of that answer, and thus 3.2 must be the right answer. So you're going to find when doing this kind of thing that it's logical which answer must be the right answer. So that'll make it easier to do. Now, the other thing we did was we discussed systems of equations, or simultaneous equations. And so we had something that was of the form ax plus by is equal to some c, and dx plus ey is equal to some f. Okay? Where x and y are our unknown variables. And so we have two equations with two unknowns. And we want to know, how do we solve this type of problem? And what I showed was one method, which is the method I use, and I have found to be the method that takes the least amount of creative thought. It's just kind of like you follow the steps and you get to the answer automatically. And that's called the substitution method. And just to remember what the substitution method says, it's a certain number of steps. First step says, take one of the equations and solve for one of the variables. Okay, so you have a choice. You could either choose the first equation or the second, doesn't matter, choose one. Once you've chosen, then you choose one of the variables. Do you want to solve for x or do you want to solve for y? Pick one, solve for that thing. You now have, let's say, x equals blah, 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 y. Next step is substitute this value into the other equation. So if you chose the first equation and solved for x, then go to the second equation, and everywhere you see an x, you plug in what you just calculated. What happens now is you're going to be left with an equation longer than the other ones, but it only has one variable in it, which means you could solve it for an actual answer. So solve this for the variable. So in our example, you would solve this thing for y. Y equals a number now. We now know the answer to y. The last step is, again, substitute this value back into the original equation. Okay? So you took the first equation, solve for x, plug that x into the second equation, you now have something for y. Y equals a number. Take that y equals a number, put it back into the first equation everywhere you see a y, and you now have a single equation for x to solve and get your last answer. So that's the substitution method. That's how I would recommend doing it. It's how I will do it when I do example problems in this course. If you have a different method that you've learned in the past that you're more comfortable with, go ahead and follow that method. Of course, make sure it's a legal method and it actually works. But if it's a legal method, you'll get the same answer as I would, having done these two different methods. So that's what we did last time. Now what we're going to do today is move on from algebra. Assume we're fairly comfortable with algebra. And we want to talk about the next big topic of math that's important, which is trigonometry. So trigonometry is very important for physics. And the reason it's important is because not so much the trigonometry itself, but the fact that trigonometry is going to, it's going to be a way of using vectors. And vectors is the important thing. In physics, and a lot of different other areas, but in physics specifically, we're going to be using what's called vectors to solve our problems. These vectors, we'll learn about them. In fact, we'll spend a lot of time on vectors because we need to be very comfortable with them. But it's some abstract concept of taking numbers, taking information, and describing them in a better way. So, for instance, I can tell you how fast you're going. I can tell you the speed of your car, 35 miles per hour. That's perfectly fine. However, what's better is telling you what's called the velocity, which tells you not only how fast you're going, the speed, but also in which direction you're traveling. So there's this one object called the velocity that tells you two different pieces of information: how fast you're going and in which direction. Now, in order to get to this vector stuff, we have to know about trigonometry, because it turns out while vectors are better in how they give information, the math of vectors is more complicated, just a little bit. But adding vectors is not the same as adding numbers. Adding numbers is easy. 4 plus 5 is 9. But if I give you two vectors, two different velocities, you can't just add them willy-nilly. There's a certain set of rules we must follow. And those rules involve trigonometry. So the trigonometry is like our way into being able to deal with vectors later on. Now, the good news is we don't need all of trigonometry. There's a vast part of trigonometry we're not even going to touch. We're only going to use certain basic principles, and that's all we're going to need. So what is trigonometry? Trigonometry is just a study of triangles. Given a triangle, what is the relationship between all of its sides and all of its angles? That's basically what trigonometry is. Now in math, when you do trigonometry, you work on all sorts of different triangles. Generally speaking, you have right angle triangles, which are nice. You've got scalene, which basically means none of the sides are the same length. And you have isosceles, which means two of the sides are the same, but one is not. And then, of course, you also have equilateral, where all three sides are the same. So trigonometry covers all of those. The special case is right triangles. So right triangles is take all the different types of triangles out there and only talk about the ones that have a 90-degree angle in them. So basically, they look like this. Triangle with a right angle. That right angle is 90 degrees. And what's nice, and what we're going to use in physics, is the amount of trigonometry necessary to deal with right triangles only. We don't care about all the other ones. And that's good because there's a lot of shortcuts, and the rules of right triangles is easier than the general rule. General triangles, you need things like the law of sines and the law of cosines, maybe double angle formula, half angle formula, all sorts of fancy stuff. None of that we're going to use. We're using the basics because the basics can solve right angles. So what are the basics? Well, we're going to have three different sets of relationships. The first set of relationships deals with the angles. So let's say we have an angle theta and we have an angle phi. Okay, so this one's theta, this one's phi. This relationship holds for all triangles, not just right triangles, but it does hold for right triangles too. And it says the sum of all three interior angles must equal 180 degrees. So if you add all three angles in a triangle, you get 180. Now if you have a right triangle, what that means is if you add theta plus phi, since the 90 degrees is already there, then theta plus phi must equal 90. Because you already have 90 here. You need a total of 180. 180 minus 90 gives you 90 left. So the other two angles must add up to 90 degrees. So that's one relationship. That relates the three angles of a triangle together. Next relationship is the sides. What's the relationship between the lengths of the sides? Well, let's say we have this side here is called A, this side here is called B, and this side C is called C. First thing to note is C is a special side. C is a special side because it will always be the longest side of your triangle. How do I know this is true? How do I know A isn't the longest side, or B? Why is C always the longest? And the reason is because the length of a side always relates to the size of the angle that's opposite to the side. And that makes sense. If you think about this, here's an angle, and here's a smaller angle. Smaller angle, the side opposite is a smaller length than here. This angle is bigger, the side opposite is longer. So if you have a big angle, then the side that's across from that big angle is going to be a big side. You have a small angle, it's going to be a small side. And what I know is that for a right triangle, the biggest angle you can have in a right triangle is 90 degrees. So since the right angle is always 90, then the side that's across from it is always the biggest side. And so we give it a special name. We call that side the hypotenuse. So C is called the hypotenuse. Okay. It's just a name for it, but it's always the side opposite the 90-degree angle. Okay, so what's the relationship? The relationship says that the square of the hypotenuse, so the longest side squared, is always equal to the sum of the squares of the other two sides. Of course, the way you usually hear this is a squared plus b squared equals c squared. Okay, that is called the Pythagorean Theorem. The Pythagorean Theorem is that theorem which relates the lengths of the three sides of a right triangle. And it says the two sides that are not the hypotenuse, if you square those sides and add them together, that's equal to the square of the hypotenuse itself. Okay? So that's another relationship. How do the three sides relate with this equation? Now, unfortunately, those two relationships are not enough to solve every right triangle problem you're going to have. You need one more set of relationships. And this one is called Sohcahtoa, or at least generally in America, we call it Sohcahtoa. And I say that because I knew in college, a friend of mine was a Chinese guy from Honduras, and in Honduras for high school, when he took trigonometry, they did not teach Sohcahtoa. They taught it some other way. I don't know what way they taught it. But in the United States, generally speaking, when you take trigonometry, you learn Sohcahtoa. If you don't know what it is, I'm going to tell you what it is right now. And if you do, then this is just a reminder. This is just kind of a mnemonic device to remember the relationships. And it's broken up into three pieces: the So piece, the Ka piece, and the Toa piece. So the first piece, SOH, says the sine of the angle theta is equal to the side opposite to the angle theta divided by the hypotenuse. So that's SOH. Sine is opposite over hypotenuse. Now this opposite thing, you have to understand what it means. What it means is, if you're looking at the angle theta, here's theta here on my example, the side opposite to theta is, of course, the side that's across from the angle theta. So in this case, B is the side opposite. The other side, A, is next to theta. And the language used in math is adjacent or adjacent. So the other relationship, the Ka part, says cosine of theta is equal to the adjacent side over the hypotenuse. So just remember, adjacent means next to. And then the last, Toa, says the tangent of the angle theta is the opposite side over the adjacent side. And that's what Sohcahtoa stands for. It's three relationships. The sine of the angle, how does the angle relate to the sides? Sine of the angle, cosine of the angle, and tangent of the angle. And so, with these three relationships, how do the angles relate? How do the sides relate? And then how do angles and sides interrelate? Then any right triangle I give you where it's missing some information, as long as you're given sufficient information, you could use these relationships to find all the missing stuff. And that's usually what you do. And so, let's see an example. How does this work? Let's take this example first. Here's a triangle. Here's my right angle. Let's say this side is 3, this side is 4. I'll call this theta, and I'll call this phi. And I'll call this side r. And so my question is, given this right triangle, calculate r, theta, and phi. So, how do we solve a problem like this? Basically, you're given tools. Those tools are these three pieces of, or three relationships. And it's up to you to put those relationships together in such a way as to solve for everything you need. So it's like a puzzle. Here's stuff like Sudoku. Here's the Sudoku puzzle. I give you some piece of information. Now you need to use that to figure out everything else. Well, here, what do we have? I've got 2 out of 3 sides. I've got 1 out of 3 angles. Remember, the 90-degree angle, I already know that one. So, I asked myself, what can I use? Well, can I use the angle relationship? That is to say, the sum of the 3 angles is 180. Well, let's say I tried it. Well, okay, the 3 angles are theta plus phi plus the third angle is 90 degrees. Must be equal to 180. Can I solve this? I don't think I can solve it, and the reason is there's 2 unknowns in this equation. I've got one equation, but there's 2 unknowns. I don't know theta and I don't know phi. And math told me a long time ago that there's no way to solve one equation with 2 unknowns. You always need at least the same number of equations as unknowns. So I can't use this yet. Maybe I can use it later, but for now I can't. All right. What about Pythagorean Theorem? Can I use that? Pythagorean Theorem would say a squared plus b squared equals c squared. So 3 squared plus 4 squared equals r squared. Remember, how do I know which one's the hypotenuse? The hypotenuse is always the side which is opposite the 90 degree. So I know the right side is the r, not the 4 or the 3. Well, yeah, I can solve this. There's only one unknown sitting there, the r, so let's solve it. 3 squared is 9, 4 squared is 16, equals r squared. So 9 plus 16 is 25, equals r squared. But of course, I don't want r squared, I want r, so I take the square root. There's plus or minus sitting there. So r becomes plus or minus 5. But I know r has to be positive. I'm talking about how long is the side. A negative length doesn't make sense. So I know the answer is actually positive 5. So I now know r. I found out one piece of information. Now, there was a shortcut. If you remember trig class, the teacher usually tries to get you to memorize some special triangles. One of the special triangles is called a 3, 4, 5 triangle. A 3, 4, 5 triangle says if one of the smaller sides is 3, the other side is 4, then the hypotenuse will always be 5. It's just an easy relationship to remember. But here, maybe the teacher didn't say. That's also true of multiples of these numbers. So if I gave you 6, 8, well, 6 is 3 times 2. 8 is 4 times 2. So it's still like a 3 and a 4, but times 2. So this must be 5 times 2, which it is. It's 10. And the same holds with multiplying by 3 or 20 or whatever. Any multiple of 3, 4, 5 also works. So, if you don't remember 3, 4, 5 triangle, that's fine. Just use Pythagorean Theorem and you get the answer. But it's just helpful to remember if you see a 3 and a 4 on a triangle, and one of those is not the hypotenuse, by the way. Look what happens if you think it's a 3, 4, 5, because maybe this is 3 and this is 4. You cannot say this is 5. That's wrong. Because remember, we already know the hypotenuse must be the longest side, and the 4 is the hypotenuse, so there cannot be another side that's 5. Every side has to be less than 4. So just be careful about that, but in general, 3, 4, 5 triangles. All right, so now we know this. R is now 5. Now what can we do? Well, now we can try some of the Sohcahtoa stuff. We know stuff about the sides. We want to know stuff about the angles. So we have to use a relationship that relates side length with angles. All right, which do we use? I've got sine, cosine, and tangent. All right, well, let's look at it. If I use, so let's say I'm looking for theta. I could say sine of theta is the side opposite. The side opposite of theta is 3 over the hypotenuse, which is 5. That's the so part. I could also say cosine of theta is adjacent. Well, the side next to the theta is the 4 over hypotenuse, which is 5. Or I could say tangent. Tangent of theta is the opposite side, which is 3, over the adjacent, which is 4. Now the question is, which of these 3 do I use? Turns out I can use any of them. All 3 will give me the same answer. However, this is a tip, not necessarily for this class, but for life in general. No matter what you're going to do. A rule of thumb is, if you can solve a problem by only using the information given to you, rather than information you calculated previously, then that's the way you want to do it. And the reason is this. Let's say I tried to use sine is 3 over 5. This would be right if, when I calculated r to be 5, that's true. It's actually right. But what if I made a mistake in my calculation here and I got r is 15? I did something weird and I got the wrong answer for r, but I don't know it. I think it's 15. Then when I go to do the sine thing, I'm going to plug 3 over 15. Well, obviously that's going to give me the wrong answer. And the same would be as I go down the problem, the more I use the information I calculated myself, the more likely everything else is going to be wrong if I made a mistake early. Now, I'm sure 5 is right, so I'm not worried. So sine of 3 over 5 is perfectly fine to use. But when you're talking about in a real world and you're doing a bunch of calculations that are all intertwined, maybe you're inventing a new drug or something and you have to do some calculations and you had to find the concentration, and then you use the concentration to find the density, and then you use the density to find the weight. Well, if you messed up the concentration, then the density and the weight calculations will also be wrong. So for me, when I look at this problem and I think about it in that way, I want to use tangent of theta, because the problem gave me the side of 3 and the side of 4, so they have to be right. So I'm not using any information that could be wrong, and so as long as I calculate this correctly in my calculator, I know this will be the right answer. For the sine or the cosine, because I'm using the 5 that I calculated, if I know I'm right, no problem. If I'm unsure, then those might be wrong even if I calculate them right in my calculator. So that's just a tip. In actuality, if you're perfect, if you calculate everything correctly, all three of these would give you the same answer, so it doesn't matter what you use. So let's try it. Let's do the tangent just for the heck of it. Tangent theta is 3 over 4. Now how do I get theta? Theta is what I want. I don't want tangent theta. So we have to figure out how to get our theta out of this equation. And I'm sure most people know how to do it already, but if you don't, I'll show you kind of what I do, or how I think about it. So, tangent of theta is 3 over 4. Think of that problem like this problem. 5x is equal to 10. And of course, what you want to know is x. I want to know what is x if 5 times x is 10. So how do I do it? Well, if we're going to think about this formally, what's happening is I'm saying there's an operation which is take your x multiplied by 5. But I don't want to do that. I want to just take my x. So I have to do what's called the inverse of the operation. The operation was multiply by 5. The inverse of doing that is divide by 5. So if I divide this by 5, then that inverse operation of divide by 5 cancels out the regular operation of multiply by 5. And then, of course, since I did it on the left, I have to do it on the right as well. And that gives me my x. Now we think about it for this tangent. It's the same thing. I've got my theta, but I'm operating on theta with the tangent. So I want to undo that operation, and to undo the operation, I do the inverse tangent. And the inverse of doing a tangent is called tan minus 1, or inverse tangent, or arctangent. They all mean the same thing. And so applying the inverse tangent to the tangent cancels them, and you're left with theta. But whatever you do on the left, you have to do the same on the right. So we have to do inverse tangent on the 3 over 4 as well. And so you get the answer. Theta is inverse tan of 3 over 4. So then you go to your calculator. Number 1 on calculators in this class, degree mode. I know math courses usually want radians. Fine with them. This is physics. We're using degrees. So make sure your calculator's on degree mode. 3 over 4, inverse tangent of that thing, gives me 36.9 degrees. Okay. Great. Now I have one of my angles. I've got one more thing to find, and that's phi. Well, now the good news is that original relationship from the top, I can now use it. I can say, now that I know theta, which is 36.9, plus phi, which is the new thing I'm trying to find, plus 90, is equal to 180. So I just want to solve this for phi. Phi is 90 minus 36.9. So 90 minus 36.9 gives me 53.1. Now note, I didn't have to do it that way to find phi. That's the fastest way. But again, that was using this number, theta, that I calculated. So if I'm not sure if that theta was right, I better not do it that way. What's a different way of doing it? Well, all you have to do is now take phi as your angle and do tangent of phi is his opposite, which is 4, over his adjacent, which is 3. And then solve this for phi, and you'll get the same answer, 53.1. So you have options. There's not one single right way of doing this. There's multiple ways of doing it. The point is you have different relationships to use, and you want to use those relationships as tools to calculate whatever it is you're trying to calculate. Any questions about that particular problem?
No.
Any question?
No, I was saying I didn't have a question about the problem.
Okay. All right, well, let's try a second example. Because not all of these are going to be done exactly the same. It depends on what information I give you at the beginning. In that case, I gave you two of the sides. But what if I give you this other example? Let's say a triangle. Here's my right angle. Let's say I know this is 30 degrees. This is 10. This side I'll call X, and this side I'll call Y. Let's let this be theta right there. And so for this problem, find X, Y, and theta. So a new puzzle, same basic steps, same relationships, but now we may have to do things in different orders. So we look at it, we say, okay, I know my three relationships. Pythagorean Theorem for the sides, the angles add up to 180 for the angles, and then Sohcahtoa if we need to interrelate them. Well, first question, can I use Pythagorean Theorem here? Anybody know?
No, because you're missing two sides.
Exactly right. Yeah. I only have one of my three, and there's no way of doing Pythagorean Theorem with only one piece of information. Because like you said, two unknowns, that's too many unknowns. All right, so no Pythagorean Theorem yet. What about the angles? Can I do a relationship between the angles?
Yep, that's right.
That's right, we can. And the reason we can is because we have the 30, we want theta, and we know those two have to add up to 90 degrees. Or if I want to write it out the long way, 30 plus theta plus 90 must be 180. But notice we could always subtract the 90 here and the 90 here. And so this always becomes 30 plus theta is 90, right? You only need these two angles. The 90 degree angle always cancels the 180 thing. So there's my relationship, and there's only one unknown. So I could solve it. Theta must be 90 minus 30, which is 60. Very nice. So now I have all three of my angles. One's 30, one's 60, the other's 90. And that happens to be one of the special triangles. You hear it a lot, 30, 60, 90 triangle. And that's what this one happens to be. All right, so now we did our angles. We have all of our angles. We have one side, and we can't use Pythagorean Theorem. So all we have left are the Sohcahtoa relationships. And so we use them. We say, right, let's look at the 30 degree angle, because that's the one given in the problem. We could say the sine of the 30 degree angle must be the side opposite. Well, opposite of the 30 is over there, which is the y, over the hypotenuse, and the hypotenuse is the 10, because it's the side that's across from the 90. And so there's my little equation. Sine of 30 is opposite y over 10, hypotenuse. So now I want to solve this for y. I get y by itself. Y equals 10 times the sine of 30. All right, so I stick this in my calculator, again making sure I'm in degree mode, and I get that y must be 5. So that's not bad. What else can we do? Well, now we have our choice. We still need to find x, and I can find x in two different ways. First way is I could continue using Sohcahtoa, which I'll show you that. To find x, x relates to the 30-degree angle by being the side next to it, so it's adjacent. So cosine of 30 is adjacent, which is x, over hypotenuse, which is 10. Solve this for x, I get x equals 10 times the cosine of 30. And I'll plug this in my calculator, and I get 8.66. And now my job's done. I found all three pieces of information: theta, x, and y. But what about the secondary way of solving for x? And that is, now we could use Pythagorean Theorem. Because notice, now we know y is equal to 5. So now we have the hypotenuse and we have one of the sides. So if I wanted to do it that way, I would say x squared plus y squared, which is 5 squared, is equal to the hypotenuse squared. And this can be done. There's only one unknown sitting there. So let's solve for x. I get x squared equals 10 squared, which is 100, minus 5 squared, which is 25. So x squared equals 75. Take the square root of both sides, and you get, let's see, 75 square rooted 8.66, of course. Which matches. It should match because we better get the same answer. These things are all related. But again, using this method here required me to use a piece of information I calculated, which was the 5. So if that 5 had been wrong, then this number would be wrong too. That's why I chose to do the cosine instead. That allowed me to use just the information given in the problem. So as long as I put it in my calculator right, I can be confident. But that's just my own little way of thinking. So any questions about this particular one? All right, so we will continue next time with trig, mostly getting into the actual vector stuff. How does trigonometry relate to vectors? What are vectors and things like that? And we're going to spend a good amount of time talking about vectors before we move on to physics, because you're going to be using vectors in this class and next semester's class as well. And if you're shaky with vectors, then you're going to have a hard time with everything, because even if you could work your equations perfectly, plugging numbers into the equations requires you to do the vectors first to get the numbers. So I want to make sure we're all really, really good with vectors before we move on. So we're going to spend some time with it. Next time, that's what we're going to get to.